Okay, good day everyone. So for today's experiment, we will perform experiment 6, energy conservation and projectile motion. The objective of this experiment is to determine the range of a projectile through the conservation of energy principle.
So, what is energy? So, energy is a property of any object or any mass that enables it to do work. For this topic, we will just talk for mechanical energies. In this energy, these are energies that due to position of an object or movement of an object. So, we are talking about potential energy and kinetic energy. So kinetic energy is the energy of motion. So it means if we will solve for the kinetic energy, velocity is involved because it will describe the motion of the object. While potential energy is the energy that something possess or that the mass possess because of its position respect to the ground. So therefore, for potential energy, this is not an energy at rest, but this is an energy due to its position. So the variable that is involved here is the height. Potential energy has a symbol of U that is equal to mass times the acceleration due to gravity times its height. So from this picture, so it will just show you that whatever the path of the object, it will just have the same potential energy because the final height of these objects are just the same, which is 3 meters. Now, from this formula, we will have the unit for energy, which is kilogram, that is for the mass. For the acceleration due to gravity, so the unit of that is meter per second squared, and the unit of height is meter. So if we will simplify this more, so that will be kilogram meter squared over second squared, or the equivalent of this is just joule. For kinetic energy, so this is the energy in motion. So it involves velocity, as I said. So the formula of this is 1/2 times its mass times its velocity squared. So the unit of this is kilogram meter squared over second squared, which is the same here. So therefore, this is also joule. Now, we will talk about the conservation of energy for this experiment. It says that energy cannot be created nor destroyed. It may be just transformed from one form into another, but the total amount of energy never changes in our system. So here, for example, this is our object. So the object jumps off from this platform. So because the object starts at a certain height, so it means the potential energy is in maximum, and since the object is at rest before it jumps off, so the velocity is zero, so the kinetic energy is also zero. So as the object moves downward, as you can see, some of the potential energy will be converted to kinetic energy until such that the object reaches the ground. Before it touches the ground, so the potential energy is zero and the kinetic energy is the maximum here. So it means the energy will just be transformed from one form into another form. So let's say this is the start of the position of our object, and this is the final point of our object. So it means, so this is the initial point. We have here the initial kinetic energy and the initial potential energy. While for this point, we have the final kinetic energy and the final potential energy. According to the conservation of energy, whatever the energy before should be equal to the energy after. So that is the total energy before, it's just equal to the total energy after. So it means we have the kinetic energy initial plus potential energy initial is just equal to the final kinetic energy plus the final potential energy. So if we will substitute the formula of kinetic energy and potential energy that we have discussed before, so it means this is 1/2 mvi squared plus mgyi is equal to 1/2 mvf squared plus mgyf. So this is the formula for the conservation of energy. So
Now for the procedure, so this is the setup of our experiment. So we have a pendulum here. So this is the mass that is hung at a certain height, and that height is the big H. And this ball will be released at this height, and then there's a blade at point B, and that string will be cut off. The height of the blade from the ground to the blade is small h. Now, once the tie or the string was cut off, it will have the initial velocity along horizontal, and it will move into a trajectory until it reach the ground. So that is now our object. So our goal is to get the experimental range. So the experimental range is the distance from the blade going to the mark. So the mark is produced in a paper with a carbon paper on top. Now this experimental range will be compared to the analytical range we have learned in projectile motion. So remember, in projectile motion, so this is the first case we have discussed in projectile motion, in which the initial velocity is only along x. And remember, the velocity along x is always constant. Now, how to get the analytical range or the delta x? So first, we have the velocity, and since this velocity along x is this is also the point of the blade, we will also call this as VB, or the velocity on point B. And that x is also, we will call this as analytical range for this experiment. And remember, in the concept of projectile motion, we always compute in two-dimensional. So we have x and along y. Now, since our focus is only for the analytical range and that is on x, we are only using one equation for solving along x, and that is the velocity is equal to delta x over delta t. So for this experiment, so we will change Vx as velocity on B, and we will change delta x as the range, the analytical range, and that is over time. Since our goal is for the analytical range, we will derive this one. So analytical range is equal to the velocity on point B times time. Now, our next problem is what will be the formula, or how can we get the value for the velocity on B? So what is the velocity on point B and what is time? To get the velocity on B, we will use the idea of the conservation of energy. So here, the conservation of energy happens from point A to point B. And the velocity we will get at point B, we will use that for our formula for the analytical range. So first, let's focus first on the ball at point A. So we have here the kinetic energy initial, since that is hang at a certain height, and also the potential energy. And as it goes to point B, it will be cut off. So therefore, we have the kinetic energy final and the potential energy at final point. So this is our initial point and this is our final point. If we will go back here for our initial point and we will use the conservation of energy formula. So we have the kinetic energy initial and potential energy initial is just equal to the final kinetic energy plus the final potential energy. And remember, the formula of that will be this one, which is based on our discussion previously. So our focus here for this experiment is what will be the initial velocity. So what will be the initial velocity at point A and also the height at point A. So for the initial velocity, since this is the start of the pendulum and usually this is hung by our hand, so the initial velocity here is always equal to 0. While the height or the initial height, which is this, is just equal to big H. Now, when the ball or when the mass go to point P, so that will be we have the final velocity and the final potential energy. For this case, we will focus on the final velocity, which is our velocity on B, and also the final height, and that is just the small h. So for here, we have the VF and the YF. And remember, as I said, the small h is just YF, while the VF is just the VB or the velocity on point B. So by substituting these variables to our equation and by canceling out, remember VI is 0, so we cancel this factor. So what is left will be M, so the mass times the gravity times the big H, the big height, is equal to 1 half the mass times the velocity on point B squared plus the mass times gravity times the small height. And by factoring out the mass and canceling it out, so since all of the factors has a mass, we can cancel it out. So that will be now, it will be now the gravity times the big height is equal to 1 half the velocity at point B squared plus the gravity times small height. And our goal is to find the equation of the velocity at point B. So we will derive this one. So from here, first, I have to transpose this factor to the other side. So it will be gravity times the big height minus the gravity times the small height. And I can factor out the gravity. So the acceleration due to gravity. So that is the acceleration due to gravity, open parenthesis, the big height minus small height is equal to 1 half the velocity on point B squared. And to remove 1 half, I have to multiply both sides by 2 to remove this one. It will be like this. And to remove the square, I have to take the roots of both sides. So the roots of the squared is just VB. So that is on the other side, it will be the square root of 2 times the acceleration due to gravity times open parenthesis, the big height minus the small height. So we have now the equation for our velocity on B. So from the equation again, before we have the velocity on B and we found out that the velocity in B using the conservation of energy is just equal to the square root of the 2 times the acceleration due to gravity times big H minus small h. And our next problem is what will be the time? Now, the time can be computed using the uniform accelerated motion formula on y since the time on x is just equal to the time on y. So remember, we will just change the symbol for our diagram. So instead of y, we will use the small h, and instead of x, we will use RA. So for y, for the time, it can be computed using the formula of square root of the 2 times the small h divided by the acceleration due to gravity. Now, since our small h here is positive, we will use the acceleration due to gravity as positive 9.8 meter per second squared. And since we have now the time and the formula for velocity, we can now compute for the analytical range. Now for the analytical range, as we substitute the value of the velocity on B and the time, and if you will look, both of them has a root, so therefore we can single this out. It will be just like this. And by just looking, we can cancel the acceleration due to gravity. That one. And this is the simplified form after canceling the acceleration due to gravity since there's a gravity here and there's a gravity in numerator and the gravity in the denominator. Then we can multiply 2, so that will be, and we can put the small h in front, so it will be the square root of 4h times the open parenthesis big H minus small h. Since 4 is a perfect root, so that is square root of 4 is just 2, we can put 2 outside. So it will be 2 times the square root of small h times open parenthesis big H minus small h, which is now the formula for our analytical range. Now again, we will compute for the analytical range for this experiment for 3 trials. So trial 1, 2, and 3. You can get the height, the big height, and the small height, and also the experimental range through the experiment. And we will compare the experimental range to our analytical range, so we have to compute for the percentage error. The percentage error is equal to the analytical range minus experimental range divided by the analytical range, and you have to get the absolute because it's always positive times 100. And after that, also show your complete solution on this calculation part and also write your conclusion based on the concept of the conservation of energy and the projectile motion of this experiment. And also answer page 62 to complete this experiment. And that's all for experiment 6, energy conservation and projectile motion.